So, in the last lesson, you read about a megastorm, and in this chapter, we're investigating temperature in storms. Chapter 1, we learned that the amount of surface water available for the sun to heat played effect in creating larger storms. At this point, though, we are looking to understand why severe storms happen. On page 49 of your workbook, you'll see a list of events that correlate to the mega flood that happened in California in 1862. The flood happened because of a series of huge rainstorms that occurred. Below is a set of weather events that caused the Great Flood of 1862. The list of weather events is not in the correct order. Put the events in the order of what happened. You can take your time, press pause, and come back to the video when you are ready. Okay, guys, welcome back. So, the order below is the correct order in which the events happened, and the sun heated the surface of the earth. We know this as something that would normally happen because we need the evaporation to happen. Energy is then transferred from the Earth's surface to the air parcel, warming the air. So as it hits the Earth's surface, it then warms the air right above it. The warm air parcel rose into the troposphere and lost energy. This, again, is the series that in any storm would take place, no matter the severity. The idea that the air parcel has to rise into the troposphere for it to cool down to go back into liquid form, which is what causes the rain. So at this point, we have the clouds forming clouds as it rose. The air parcel stopped when it reached the same temperature as the surrounding air high in the troposphere. So as we know, if something is warmer, it's going to need to go up further to release the energy because it's releasing energy as it goes, but since there's more energy, it's going to take longer. A lot of rain fell and then severe flooding. At this time, I would like you guys to pause the video and go back and reread the disaster in California. We want to solidify our understanding of what causes large amounts of rain. Before the Great Flood of 1862, California's weather was constantly hot and dry. Then in 1862, it experienced a series of large rainstorms that caused a mega flood. You're going to focus on the changes that occurred to cause change in rainfall, resulting in the Great Flood. When you are finished rereading, please join back. Welcome back. So, I would like you to turn to page 50, and we're going to discuss some of the questions that correlate to the reading of the disaster in California. And why did the warm air temperature lead to more rainfall? What happened when the air parcel rises higher in the troposphere? And when does the air parcel stop losing energy? Well, when did the warm temperatures lead to more rainfall? Warmer air means more evaporation and more water vapor in a parcel. So warmer air parcels also rise higher in the troposphere, so they lose more energy and cool more. So we have warmer temperatures, right? So if it's warming up the water vapor to a higher temperature, that means it would have to go to a higher level in the troposphere, which kind of leads us into the second question. And what happens when the air parcel rises into the highest troposphere? So when the air parcel rises in a higher troposphere, it enters colder and colder temperatures. It changes the temperature more and it loses more energy to become stable. The more energy it loses, the more it cools and the more liquid water condenses, leading to more rainfall. So as it goes up into the troposphere, it's getting to colder and colder temperatures. If it's continuously getting into colder temperatures, that means that the air parcel is going to become a colder temperature than if it was at a lower troposphere. Meaning because there's more energy, it's continuously rising. And because it's continuously rising, it's getting into an area where it would have to release more energy to be equal. So, and that goes into our last question of when does the air particle stop losing energy? And this kind of goes into like previous units where we understand that temperature has to be equal to the surrounding air. So things stop exchanging there's a stop of an exchange of energy when the temperature of the air around it are equal. So I want to introduce the word pattern. So this is something we observe to be similar over and over again. So when we look at weather patterns, we're looking for something that's constant, something that kind of leads us to a prediction. This again is going to be a question inside of the quiz. So scientists often look for patterns in the natural world. Looking for patterns is one way that scientists and others can understand the evidence they are collecting. Weather scientists look for patterns in weather, such as the conditions that add up to cause a larger rainstorm. For example, when scientists identify a pattern of warmer temperatures and more water vapor leading to more rain, it might help them predict when there will be more rain when they observe the same conditions at another time. So this is something that I wanted to show you in class, but if we were to take the temperatures of every day, we would notice a pattern that usually when we have a hot day followed by a cold day, the following day would end up a result in rain, or even vice versa. So it's not, there's a lot of other conditions, but it is something that is observable. So we're going to go back and we're going to look at a simulation of causing larger rainstorms. You're welcome to turn to page 51 and try the experiment on your own, but I will be leading the simulation as well. And our question is, what determines how much an air particle will cool? So we're keeping that in mind. We want to know how much, what determines the air particle cooling, because if we know when and if it will stop cooling, we'll know how much rain will be attached to it. So we're here in the simulator. And I want to remind you that we're investigating what determines how much an air particle will cool. In the article, you read about what caused the change in the California's rainfall, which led to the Great Flood of 1862. For example, we learned that when an air particle rises higher in the troposphere, its temperature changes more as it loses more energy and cools, which can cause more rain. We are going to use the simulator. You're welcome to try to use the simulator prior to watching the rest of this video, but I'm going to do the experiment as well on this video. And you should turn to page 51, 52 in your notebooks. And what we're going to do is we're going to try to understand a different way to increase the amount of rainfall. In chapter 1, we focused a lot on the surface water. And today we're going to focus more on the temperature of that water. So I'm going to bring the surface level to 5 because we already know that the lake was built. And this would be a more accurate representation of there being a lake. So if you want a cloud with more severe rain, I would need to have a fairly large amount of energy transfer. So if I want more rain, I would want more condensation, which means I would want more energy. So I'm going to increase, instead of being at level 3, I'm going to increase it to a level 4. And I'm going to watch what happens here. We see that the sun is hitting the lake more and rising the temperature to a higher degree, to 35 degrees Celsius. And it continues to rise until it gets to negative 30 in both the air particle and the temperature. Now I'm going to go back to the analyze because I want to show you some key parts here that will make this a little bit easier to understand. So the highest temperature is 35 degrees Celsius. That is what the water vapor reaches. And right now, the outside temperature of the air particle is 15 degrees. Now, I want to get the air partial to 15 degrees. So it's going to rise. And right about here, it's at 15 degrees, which was the original temperature on the ground. But as we see, when it gets to 15 degrees, it's higher in the troposphere. So now the troposphere is -5. So it's not equal yet. So even when we reach -5 in the air partial, let's get to -5. Now the outside temperature is -20. Because there's more energy, it's requiring more to cool off. And as it rises up and up into the troposphere, the temperature it needs to reach continuously gets lower. Then it reaches -30, which is where we have the rainfall. And as you can see here, it rises to a severe level of rain. So I want you to record these temperatures into your notebook. You're going to have to record that the partial goes to 6.5 kilometers. The temperature is -30 degrees. The starting air temperature was 35 degrees and the final was -30, and the difference between them is 65, and the energy transfer out is 168 megajoules. If you didn't catch all that, that's okay, because I'm going to put the information onto a slide. Now, I want you to think, what can you change about the sunlight to get a moderate amount of rain? And so that's what we're trying to go for. We're actually at severe. So we want to see what would bring us actually down to a moderate amount. I'm going to go back to the build. And just give me one moment. So I'm going to go and I'm going to bring this down to a 2. So I'm bringing it down because we want actually to lower the amount of energy. So if I lower the amount of heat, I'm lowering the amount of thermal energy that's being transferred onto the water. I'm not changing the surface water because we're actually not focused on the amount of surface water. We're more focused on the temperature itself. So as you can see here, I'm rising it up. It goes to 25 degrees Celsius, and it actually stops at 5 kilometers. So last time the rain stopped at -30. Now that there's a less energy being transferred, it had us cool to a lower temp to a less severe temperature, which was -25 versus the -30. And if we go to the Analyze tool, we see again, we lowered it down to a moderate amount. Now, let's say I want to make it even more severe. So we started at 4 with our first study, and I'm actually going to move it all the way to 5 and run this. And now it's going to a higher temperature. The starting temperature on the bottom is now 40 degrees. And it requires it to get all the way to -35 to be equal with the outside temperature. And if I analyze that, that gets us to a very severe storm. Now I'm going to go back to the slides. Back at the slides, and I've recorded all the data. If you need to take a second to press pause and write this down in your notebook, this will be helpful. So, and some questions I have for this is, what causes the air partial to stop rising? And what happens is that it has to equal the outside temperature. It stops when it's -25 degrees, and that's the final air partial. So you notice that these are exactly the same. That it stops when the final temperature and the troposphere temperature are exactly the same. And what test did it rise the highest? And it rose the highest when it was here at 7 kilometers. And if we look here, the air temperature was 40. So we're looking for a pattern. When it was the second highest, which was 6.5, it was 35 degrees at the starting temperature. And the third, or the lowest, was 5 kilometers, and the starting temperature was 25. So we can see the pattern is that the higher the temperature it is at the initial, when the air partial starts to rise, when it's higher, it goes to a higher level of the troposphere. Now, I want you guys to make sure you understand this concept, and I'm going to go over this in the online session, the live session, because I want you guys to really understand that an air partial rises, energy transfers from the warm air partial to the cold surrounding the air until their temperatures become equal. And when an air partial starts with a higher temperature, it will rise higher and lose more energy, causing more rainfall. So again, this is key. This is key to understanding. Go back into the simulator to show this issue here. So this is with the severe storm, and it reached 40 degrees Celsius, right, at its highest temperature. Now, this is 15 degrees. So the original outside temperature is 15 degrees. I want to wait till this gets to 15 degrees. So as we go up into the troposphere, it's about here that it gets to 15 degrees. You notice that it doesn't stop because now it's higher in the troposphere and the outside temperature is -5. It's no longer 15. So it has to continue to rise and cool and release the energy. And it won't stop until both of these are the same temperature. Now that it's at the same temperature, there's more liquid rain because more of the energy was released. So after this, I want you guys to fill out the quiz. It includes the homework pages, and I will see you guys when you guys come to the live video checks. I really want to explain this part and make sure everyone understands this.